Hello, and welcome to the CU Boulder Retired Faculty Distinguished Professor Seminar Series. Some housekeeping rules before we get started. All attendees' microphones will be muted. Questions are encouraged via the chat box. Click the chat icon at the bottom of the screen. Message to everyone is okay. All questions will be answered at the end of the talk. The seminar will be recorded and available on the Boulder Retired Faculty Association website. And now I will be turning it over to Dave.
It's my pleasure as the chair of the Retired Faculty Association of the Boulder campus of the University of Colorado to introduce this eighth in a series of presentations by our colleagues who have the rank of distinguished professor. These are very, very special people, and the seminars and the presentations that have been given, including one piano performance by David Korovar, have been wonderful, and people have appreciated the contributions of our distinguished professors. So without further ado, let me introduce the chair of the Astrophysical and Planetary Sciences, Nils Halvorsen, the chair, and he will continue this introduction.
All right, thanks, David. So my name is Nils Halvorsen. I'm a professor and chair of the Astrophysical and Planetary Sciences Department here at CU Boulder. I just wanted to say a few words about our department. Our department has over 350 undergraduate majors. This major has doubled in size over the past decade and is now the largest astronomy undergraduate major program in the country and likely the world. We have 60 graduate students and 28 faculty who conduct research in cosmology and galaxy evolution, black holes, stellar structure, exoplanets, planetary sciences, solar physics, space weather, and more. Our campus facilities include the Summers Bosch Observatory, which features 2 new 20-inch telescopes open to the public every Friday night, and the Fisk Planetarium pictured behind me here. Please reach out to me or visit our campus facilities or our campus webpage to learn more, and that's http://www.colorado.edu/APS. And finally, I'd like to mention that Professor Emeritus Kim Melville, a former chair of our department, now retired, arranged the talk. He has the highest regard for Professor Begelman, who he considers a friend as well as a colleague. And now I'd like to turn it over to Chancellor Phil DeStefano, who will introduce our speaker for this evening.
Thank you, Nils, and good afternoon, or actually good evening to everyone. It's a pleasure for me to be here and to be part of this wonderful series put together by the Retired Faculty Association. It's my pleasure to introduce our speaker this evening, Dr. Mitch Begelman. Mitch is a professor of astrophysical and planetary sciences in the College of Arts and Sciences. He's made influential contributions to high-energy theoretical astrophysics. His groundbreaking papers on the origins of radio sources from outside the Milky Way, primordial quasi-stars, and the astrophysics of black holes are pivotal contributions to our understanding and evidence of black holes. Mitch holds many national awards, including the Guggenheim Fellowship, the Helen Wellner Prize of the American Astronomical Society, an Alfred Sloan Foundation Research Fellowship, and a Presidential Young Investigator Award. He was awarded the American Institute of Physics Science Writing Award for the book that he co-authored titled Gravity's Fatal Attraction, Black Holes in the Universe. It's my pleasure to introduce distinguished professor Mitch Begelman. Mitch?
Thank you very much, Phil. There, you should see my title slide. Okay, I'm going to talk about why black holes are fussy eaters and why that's actually important. My talk is mainly about what black holes do to their surroundings, but I think first I better tell you something about what black holes are. So let's start with that. Fortunately, the simplest dictionary definition of a black hole you might find is actually pretty good. Here it is: a region of space having a gravitational field so intense that no matter or radiation can escape. The surface of no return, from within which nothing can escape, is called the event horizon. And it's how the event horizon actually accomplishes this that makes black holes so weird and maybe a bit scary. In fact, I think that the existence of event horizons and even the possibility of black holes is the most surprising prediction of Einstein's general theory of relativity, which is the theory we have for how gravity works. But how an event horizon actually works is even weirder than how it sounds. The general theory of relativity tells us that gravity is a manifestation of the distortion, the curvature of both space and time. And it's really, I think it's impossible to visualize all aspects of this, but you can sort of make some analogies. And one of the ones that I think people are most familiar with is the idea of a rubber sheet, in which you can actually stretch out space. And what happens close to a black hole is that space itself is infinitely stretched and is being pulled through the event horizon at the speed of light. So the reason you can't escape a black hole is you're allowed to go up to the speed of light relative to space, but you can't go faster than the speed of light relative to space. And space itself is being stretched and pulled through the event horizon at faster than the speed of light. And so you can't get out and nothing can get out. Moreover, there's a stretching effect. Space is not only being pulled, it's being stretched as it's pulled. And so effectively, an object that has fallen through the horizon and you're seeing it disappear from outside is being pulled infinitely far away. So objects falling through the horizon from the point of view of an outside observer are effectively infinitely far away. And that's really responsible for the effect that if you were to be able to watch someone fall through a black hole, you wouldn't see them just continue falling and then, go into blackness. You would actually see them kind of freeze and fade out and just sort of disappear. A corollary of this is that there are no trajectories that a real physical object or a light ray can have inside the horizon that actually points outward. All trajectories point inward. Okay, so that's a little bit about how black holes work, but what I'm mostly going to talk about is what, to me, as an astrophysicist, is really most amazing about black holes, and that is that they exist. And we have loads of evidence for them. We're studying them in a great deal of detail now. And maybe you find it a bit worrisome that these things are actually rather common. We can do a census of them, starting with our own galaxy, for example. Here is an image of a real galaxy. It's kind of what the Milky Way would look like if you were looking down on it from outside. And if this were the Milky Way, the sun would be about here. This is actually a disk, and there's a halo around it, but most of the action is occurring in a sort of a flat rotating disk. The sun would be about here, and in this region of the disk, we are pretty sure there are around 100 million black holes, each one having the mass of a few tens of the mass of the sun. So the Milky Way and every other galaxy like the Milky Way and every other galaxy basically is chock full of black holes. But that's not, and if you work out how far the nearest one is, it would be less than 100 light years away. 100 light years is not all that far. The entire disk here is tens of thousands of light years away. So the nearest one would be around here, maybe. Okay, there, another one. In addition to that, at the center of the galaxy, which is kind of obvious here, that's where the stars are most concentrated, there is one giant black hole. That black hole is 25,000 light years away. Okay, so in the middle of the Milky Way, there's this giant black hole, small black holes everywhere in the Milky Way. Well, how do we know about any of these black holes, but in particular, this giant black hole? Well, this is a time-lapse movie of the center of the Milky Way. There's a lot of dust and gas between us and the center of the Milky Way. So with an ordinary telescope, you can't really get this view. But if you have an infrared telescope, and we have quite a few big infrared telescopes now, you can see through the dust. And if you do a time-lapse image, you can see the stars moving around. Now, if you look carefully, you can see that these stars are not moving in straight lines. Some of them are undergoing curved paths. And this curved path is due to the gravitational field of whatever is in that region acting on these stars. And the way we know that there is a giant black hole at the center of the Milky Way is by tracking the orbits of these stars in that as they move under the influence of the black hole's gravity, and figuring out how much gravity has to be there and how much mass has to be present. Now, it's nice to watch a time-lapse movie, but of course, if you want to do this properly, you have to analyze it mathematically by actually plotting the trajectories of all these stars, and that has been done. This image starts in 1995 and ends up just a couple of years ago, and what you can see is that these stars are indeed moving on curved paths, but not only that, they are very regular shaped curved paths. And in particular, there's one star here which has actually been observed to go through more than one closed orbit. And if you analyze the path of this star and all the other stars, you will see that they are orbiting the focus of a single, very compact point of mass, which has a mass of 4 million solar masses, and it's located at the position of the star. Okay, now, there is no way you can have 4 million solar masses of stars in such a small region. In fact, we can confine this 4 million solar masses to actually a region that's even smaller than the size of the star in this picture. So there is really no alternative to just saying that it's all in one tiny lump. And the simplest explanation for what that lump is a black hole. And it was for the discovery of this 4 million solar masses all concentrated at a point, which really must be a black hole, that the Nobel Prize, half the Nobel Prize in physics last year was awarded. This is for the discovery of the Milky Way's giant black hole by Professor Andrea Ghez from UCLA and Professor Reinhard Genzel at the Max Planck Institute in Munich. And they basically did very similar things, competing with each other over a couple of decades, and came up with the same result, which is really great, because if you're going to claim to have proven something this weird, it's better to have a lot of confirmation. So the presence of a giant black hole at the center of the Milky Way has been, at least its gravitational field, has been verified by actually tracking the motions of stars. But you might want more evidence for that. You might ask, can we actually image the Milky Way's black hole? Well, that's pretty hard. In fact, since we know how much mass is at the center of the galaxy, we can actually work out how big that black hole would appear on the sky. And if you do that, it turns out that it would appear to be about the size of a grapefruit on the moon. So it would be like being able to see a grapefruit on the moon. That sounds impossible, okay? I don't think this picture of the footprints was taken by one of the astronauts, not by a telescope from the Earth. But in fact, we expect a photo of the Milky Way's giant black hole very soon. And by very soon, I mean the data have been taken and they're being analyzed. And the telescope that allows us to do this is called the Event Horizon Telescope. It was put together specifically for this purpose. And what it is an array of radio dishes that basically are scattered across the hemisphere of the Earth. Now, you can do an amazing thing with radio telescopes. You can actually combine their signals so that they all, you can make their signals work together so that it simulates a single dish. These are all, of course, normal sized radio telescopes, tens of meters in diameter. But this array of radio telescopes simulates a single dish that would be the size of the hemisphere of the Earth. And the bigger your dish, your telescope, the finer details you can see. So this telescope working at in the millimeter part of the electromagnetic spectrum can actually get the detail needed to see the to actually image the black hole in the Milky Way. Now, I said we don't have the Milky Way black hole image yet, but we do have another image that was taken by this telescope. The first image taken by this telescope was actually in the galaxy M87, which is a galaxy much bigger than the Milky Way. It's 2,000 times further away than the center of the Milky Way, but the black hole at the center is 1,500 times bigger. So this black hole is actually smaller on the sky than the black hole in the Milky Way, but it can be mapped because it's nice and stable and it doesn't flicker very much. The reason the Milky Way's black hole has been so hard to image is that it actually flickers a lot in the course of an hour or so, and that actually makes it harder to make an image. Now, on the left-hand side, you can see the actual image that was reconstructed from this telescope, and it shows a shadow in the middle, so black holes really have a black center. And what you're seeing here is a ring of light produced by, it's radio light. It's being produced by gas that's swirling around this black hole, very energetic, and it's glowing, and that is relevant for the story I'm going to be describing later in this talk. The right-hand side is a theoretical prediction of what the left-hand side should look like, and if you blur it out enough, you can sort of see that it's a pretty good match. So we have actually imaged one giant black hole, and that black hole would appear the size of an orange on the surface of the moon. So we're doing pretty well. Now, there they are, comparison. Now, we do have some data about the structure of what's going on around the center of the Milky Way, because an infrared version of this radio experiment, an infrared version of the Event Horizon Telescope, has been constructed on the top of a mountain in Chile. And what's happening here is that each one of these buildings houses the infrared equivalent of a radio dish, and the images from all these telescopes can be combined. And because infrared rays have a much shorter wavelength than radio waves, these distances are enough to simulating a dish this big is enough to actually get you the detail you need. Now, the problem with this instrument is that it's not really good at making actual pictures, but it's good at pinpointing motion of spots where radiation is being emitted. And what this telescope has seen is spots of radiation orbiting the location where we have deduced the center of the Milky Way's black hole is. And so we do have some data on that, and hopefully that will be bolstered when the Event Horizon Telescope image is produced. And I guess it's circulating in a clockwise direction. And I should say my colleague in APS and JILA, Jason Dexter, is one of the key theorists working both on this project and on the Event Horizon Telescope. So he's actually involved in making these images. Now, black holes have also revealed themselves in other ways, and I just want to mention the most dramatic of these, and that is through the production of gravitational waves. So Einstein says that gravity is a curvature of space-time. And if you change the gravity, say by having two stars orbiting each other, and best of all, two black holes orbiting each other, you can change gravity very dramatically. And the change in gravity doesn't appear everywhere in the universe. The signals from those orbits actually can only travel as fast as the speed of light. So two black holes orbiting one another actually produce traveling ripples of space-time, which are called gravitational waves. Here's an animation using that rubber sheet analogy to sort of show you what happens. These ripples of gravitational waves actually carry away energy, just like waves of light carry away energy. And the black holes have now merged because the energy carried away by these ripples has to come from somewhere, and it comes from the orbital motion of the black holes around each other. So gravitational waves make black holes that are orbiting each other eventually merge, and as they merge, they send out this traveling signal, and the signal is kind of a ripply thing like this. And as these gravitational waves pass by, it acts like a fluctuating gravitational field. Well, if you have a pendulum in the path of these gravitational waves, and these waves are being produced by black holes that might be billions of light years away, they travel all the way to us, and everything on the Earth is subject to these ripples of gravity, including this pendulum, which is inside the LIGO Gravitational Wave Observatory. So the ripples of a binary black hole merging into a single black hole billions of light years away will cause this system of suspended weights to wiggle in a precise way by an amount equal to about 1,000th the size of a proton. And by the way, a proton is really small. It's like 1/10,000th the size of an atom. So it's 1,000th of a 10,000th of an atom. Believe it or not, the 3 of these detectors are constructed, and they are able to detect these ripples. In fact, the first detection was made in 2015, and here is the measured signal from 2 different detectors. So you want to see this in more than one detector to make sure it's real. So one of these detectors is in Louisiana, the other one is in Washington, and these 2. The third one that's operating now is in Italy. Here's the measured signal from the first detection. Here's the predicted signal. Not bad. This is so good that people saw this on the data without even analyzing it very much. You know, it sort of jumps out at you. This signal has now been seen dozens of times since the first detection. We have now seen the signals from 47 pairs of merging black holes, last I checked, 2 pairs of merging neutron stars, and 3 pairs of neutron stars merging with a black hole. Okay, now, these signals are from stellar mass black holes, tens of times the mass of the sun. They're not from giant black holes. We see the direct evidence of the giant black hole in the Milky Way and in M87, and we're sure there are these giant black holes in almost every galaxy. So black holes, these strange things predicted by relativity, are common. Okay, so should we be worried about these black holes? Are we going to fall into them? Okay, no, emphatically, no, not a problem. Common thought is that, you know, well, I hope the sun doesn't become a black hole, we would fall into it immediately. Well, we might get pretty cold, or we might get irradiated by gamma rays, depending on what happens close to the black hole. But one thing we would not do would be to fall into the sun if it became a black hole. We would just continue to orbit the black hole just as we're orbiting the sun. And that's because black holes do not behave the way that many of us like to think, that they are somehow cosmic vacuum cleaners, and once you have a black hole, it's all over. The entire universe is going to fall into it. And that is exactly because of the same effect, the same feature of the Milky Way's big black hole that I was just talking about. It's really tiny. It's a very small spot on the sky, about the size of a grapefruit at the distance of the moon. They are very small targets. To fall into a black hole, you have to get close to this event horizon. And it is really hard to aim well enough, if you want to get close enough to a black hole as the event horizon. To give you an idea of how small a black hole is, the nearest stellar mass black holes are probably about 100 light years away, and their size is about 10 kilometers. So your target is 10 kilometers at a distance of 100 light years. That's actually much smaller than the size of a grapefruit or an orange on the moon. The giant black hole at the center of the Milky Way is 1/10 of the Earth's orbit, the size of the Earth's orbit, at a distance of 25,000 light years. So think something that's about 10 times the size of the sun, but 25,000 light years away, also very tiny. So even if you aimed carefully, it would be almost impossible to get close enough to these black holes so that you'd be sucked in. That is not to say that black holes are not swallowing stuff. And there are two really great ways to feed black holes. One is to have a black hole with a nearby star orbiting it. Well, star orbiting it in a pretty tight orbit. This is a pretty fanciful artist's impression of a black hole with very weird colors. The black hole is meant to be at the center here. There's jets coming out, and I'll talk about those later. And this is supposed to be a star. Maybe it's a red giant or something like that. Gas is being pulled off this star by the gravity of the black hole and swirling in a disk around the black hole and presumably getting into the center. And this is happening. We see several dozens of examples of this happening in our galaxy. And it is, in fact, the way that black holes were first discovered more than 50 years ago by X-rays emitted by this swirling gas. Another thing that can happen is a black hole could simply be located in a place where there is a lot of debris in the form of gas clouds collecting. Now, there is debris between the stars in our region of the Milky Way, but there's not all that much of it. You'd have to be really lucky to have a black hole which was situated where it could swallow a lot of gas. But in the center of the galaxy, that's the center of mass, there's a tendency for gas to settle into the center. And the black hole at the center of the Milky Way is pretty well placed for swallowing some of that gas. So it is possible for black holes to swallow gas, but even if you get black gas close to a black hole, it's a little bit tricky to get that gas to go through the horizon. And the reason is that even if you aim very well, it's very difficult to get that gas to fall straight into the black hole. It gets deflected. And that's because you not only have to aim very well, but you have to make sure that the gas is kind of, well, pretty much it's an aiming problem. You have to make sure that the gas hits the black hole straight on if you want it to go straight in. If there's any slight deflection, that deflection will get amplified as this material gets closer and closer to the black hole. And instead of going in, it will swirl around the black hole as shown here in this simulation. So this is a more realistic view of what would really be happening if a black hole were tearing material off that red sort of weird looking star in that artist's impression a couple of slides ago. So you see the gas is not really going into the black hole, it's swirling around and it's very, very turbulent. This swirl, what we really mean is that there's too much angular momentum. So gas approaching a black hole, even if it gets pretty close to the horizon, maybe 100 times out, reasonable aim, even then it won't go straight in. In fact, it forms a disk swirling around the black hole called an accretion disk. Now, an accretion disk, I like to think of an accretion disk as kind of like a gaseous equivalent of a whirlpool or water going down a drain, except in most cases, the disk is thought to be pretty flat, although not in all cases. It might actually have this three-dimensional shape as shown in this, this engraving by the illustrator Arthur Rackham from 1935. Now, the thing is that if you have a bathtub or a sink full of water and you pull out the stopper, it forms this this vortex, this whirlpool going around the drain, but eventually it goes in. Well, the reason it goes in, the reason it forms the vortex is that even though the water looks still, there's enough disturbances to give it a little sideways swirl. So when I say it's hard to get the gas going straight enough into the black hole so it goes straight in, I'm serious about that. Even if you let a bathtub sit, there's enough little bit of motion, and that's enough to actually prevent the water from going straight down the drain. But the other thing is, the fact that it goes down the drain at all and doesn't just sit there forever is because the water actually has a little friction in it. So you need a little bit of friction to get rid of that angular momentum. Otherwise, the angular momentum will stay there forever. And friction in a liquid or a gas is called viscosity. So you get this accretion disk, and the only way the stuff in the accretion disk can get into the black hole is if it is a little bit of gaseous friction or viscosity. Now, what this viscosity does is it allows the gas to get rid of its angular momentum and drift closer and closer to the drain or the black hole. And as it does so, there's a conversion of energy from one form to another. So there's a story of motion here, and tied to this motion is an energy conversion story. And here is a diagram of how the flow of energy works in an accretion disk. Ultimately, gas that's approaching a black hole is going to be pulled in by gravity, and it's going to acquire a lot of energy from that. And as the gas gets closer and closer to the black hole, it swirls faster and faster. And so it acquires energy of motion, which is called kinetic energy. But the only way that the gas can get closer and closer is through the action of this viscosity or friction. And as I'll say in a little bit later, this friction is related to turbulence. And friction does a second thing besides merely allowing the gas to get rid of its swirl or angular momentum. It generates heat. So, you know, when you rub your hand along a hard surface, a little bit of heat generated, or you get a rope burn. Okay, that's effective friction. Same thing happens in an accretion disk in gas. And so you generate heat, and it's impossible to avoid that. And hot gas glows, so when you have heat, you generally have radiation. And in the case of gas swirling around one of these stellar mass black holes, that radiation comes out in the form of X-rays. Well, we know something about how this friction works, and it turns out that it's a little bit more complicated than with an ordinary gas, where friction is just due to the motions of the molecules. The friction in the gas swirling around a black hole, it turns out, is due to the action of magnetic fields that get amplified in this gas and tangled up. And we can simulate that action. And you can see that it sort of behaves like a friction, allowing the gas to get closer and closer to the drain hole and eventually get swallowed by the black hole. At the same time, you see the gas is puffing up here because it's getting hotter and hotter. And in this computer simulation, we're not allowing the gas to radiate. So of course we can do whatever we want in a computer simulation. But in a real accretion disk, what would generally happen is that the gas would swirl towards the black hole. A lot of the energy would go into heat. It would radiate. You'd get X-rays out, and we can measure those X-rays. But that's not what always happens. And in fact, in a surprising fraction of instances, it looks like this last step from heat into radiation, light basically, whether it's X-rays or ultraviolet or some other form of radiation, this last step is the most fragile, and it gets broken. And if that happens, you end up with a lot of heat, but nowhere for it to go. So in many black holes, and probably the majority, what happens is a small amount of this swallowed matter that gets really close to the black hole and maybe close enough to go in, liberates its energy, but that energy is in the form of heat. It can't get converted finally to radiation and just fly away, leak out. Hot gas has a lot of pressure. It's stuck. It goes back into kinetic energy by just pushing the gas around. But the gas it pushes around is different than the gas that released the heat. And so what you get instead is inflow coming through parts of the disk, but outflow going through other parts. So you have a new energy chain, which sort of looks something like this. This is a pretty rudimentary simulation from a few years ago, where basically you have the gas being pulled in by the black hole. It's swirling around, and it's very turbulent because of the action of these magnetic fields. It's not radiating. The energy is going into the outflowing gas. And so you get this new energy chain of gravity, energy from gravity going into energy of motion, going into heat, and going back into motion. Hence, unless you have a perfect energy chain where all of the heat radiates away, and that is, it appears, as the exception rather than the rule. What happens mostly when gas gets close enough to a black hole to do this is that a small fraction of the gas gets swallowed. That releases a huge amount of energy, which goes into the remaining gas, and that remaining gas flies away. Hence, my title, black holes are generally fussy eaters. So it's hard to feed black holes for two reasons. One is, unless you have a very special situation, you don't even get the gas close enough to the black hole to start this process. But even if you do, most of that matter is going to be blown away because you release so much energy that a small amount of energy of matter being swallowed by the black hole is enough to release the most of the material that's trying to get in. Okay, so let's talk about a little how that works in a little more detail. Here is a somewhat more sophisticated simulation in which the investigators, McKinney et al., put in all the effects of magnetic fields. And unfortunately, it's slowing down here. That's not good. Let me see if I can, yeah, that's. Okay, so what you see is the effect of energy being released in this very bright region near the center. That energy is being deposited along the axis above and below, and here it's getting a little bit unstable. And it's not even coming out sideways, it's being focused into a jet. And that is a direct effect of what magnetic fields do, which I'm going to show you in the next animation, which is just a different visualization of this same calculation. This effect is because the way magnetic fields act is not simply just, it's not like heat, hot gas expands, exerts pressure, pushes some other gas away. Magnetic fields transfer energy from one piece of gas to another in a very specific way. I like to say that magnetic fields act kind of like a cross between a rubber band and a spring. Okay, so if you try to stretch a rubber band, it pulls back. So if you try to coil a magnetic field into some kind of a loop or a loop-like structure, it'll pinch. So magnetic fields try to twist themselves up. But once they twist themselves up, you get a coil. And what does a coiled magnetic field do is it behaves like a spring. It's like a compressed spring. So magnetic fields like to twist themselves up and pinch sideways, but they like to spread out lengthwise and push in a particular direction to the direction of the coil, the axis of the coil. And that gives you this jet. It's basically being pinched from the side and pushed out parallel to the axis. And you can see that very nicely here, where instead of visualizing the gas, we're going to be visualizing the magnetic fields that are coming out of the top. And so the magnetic fields here are being coiled because the gas is swirling around. And as it gets coiled, it forms a spring, which is pushing outwards. And the blue shows where the gas is getting pushed. Now, these simulations, of course, are all in a computer, and we need computers to do this because these processes are very complicated. You can see how much variability there is with time. It's very difficult to model these things with very idealized equations. You really can't be sure you've analyzed it correctly until you can sort of get a more detailed picture of this. So you might say, well, this is still something that we're imagining these effects, and we certainly don't have all of the physical processes put in. So do we see anything like this? Well, here we go. This is the nearby galaxy Centaurus A seen from the side, and so these dark bands here are those clouds of dust that prevent us from seeing directly to the center of the Milky Way, because we also have bands of dust in our galaxy. But popping out of this galaxy, you see something that looks not too different from that movie. Okay, so, and you could sort of see that this is going to have a dramatic effect on the overall structure of the galaxy. So these jets contain a huge amount of energy. They pump a lot of energy into the galaxy, and they can inflict a lot of damage on a galaxy, and not just on a galaxy, but even on a whole cluster of galaxies. So here is an image of the cluster of galaxies, the main cluster of galaxies in the direction of the constellation Perseus. And these yellowish blobs here, each one of these is a galaxy. Each one of these is actually bigger than the Milky Way's galaxy. So these are imaged with the Hubble Space Telescope. I think. And the rest of the stuff is X-ray radiation. And so in between the galaxies, there is this atmosphere, and this atmosphere is very hot, and it's being heated further and stirred up by jets coming out of the center here. And you can can't really see the jets in the center, but you can see these sort of dumbbell-shaped lobes on either side. That is the equivalent of these two regions here that you can see in the previous picture. So this is a case where even more energy is coming out. And if you sort of flash between two different visualizations, in this image, you see the holes punched by the jet that's emerging. But in this image, you can see how much it's stirring up and making the gas turbulent. And here, the distances are absolutely vast. This is 250,000 light years on this bar here. So you're talking about 1 million light years from there to there. Now, the energy released by a black hole growing in the center of the Milky Way in M87 in early days when the galaxy was forming would have been huge. Right now, the Milky Way's black hole is not doing too much because it's actually not swallowing very much. But it had to swallow a lot of gas at some point because it had to grow to its current size. You can't just grow a black hole, it turns out, by merging a lot of smaller black holes. At some point, you've got to throw a lot of gas into it. If you work out how much energy would have been released in the entire history of the Milky Way's black hole or any of these other giant black holes, it's about 10 to 100 times more than you need to blow all of the unconsolidated gas, the gas that has not yet formed stars, clear out of the galaxy. So that's a problem, because early in the history of galaxies, the stars that we have around us have not finished forming yet. And if you were to blow all the gas away before it forms stars, you don't have that gas anymore to form stars. So that maybe there's a problem here, or maybe the theory's wrong. If we believe in this feedback effect, something like this must have happened at the center of the Milky Way. And in fact, there is some evidence of a smaller version that might have happened fairly recently. The Fermi Gamma Ray telescope has actually seen gigantic bubbles emerging from the center of the Milky Way. And this is it's a pretty rough image. This white stretch along the middle here, that's the disk of the Milky Way. Center of the Milky Way is right along here in the center. And these bright orange patches here represent a huge amount of hot gas extending several thousand light years above and below the center of the Milky Way. So this would not have been an explosion in the early history of the Milky Way. This would probably be a few million years old, maybe 10 million years old. But it represents a large amount of energy that very possibly could have been the result of an episode a few million years ago when the Milky Way's black hole, which is now very quiet, suddenly woke up and got fed for a while and produced a huge amount of energy. Now, smaller episodes may have happened even more recently. Here's a picture with the radio telescope recently constructed in South Africa called Meerkat. This is in radio waves, not gamma rays. And this is the very center of the Milky Way. So this is maybe 100 light years across. The Milky Way's black hole is right in this bright spot there. And you see above and below it these kind of very faint outline of some eruption, which might have been something that happened maybe a few thousand years ago. Well, people recognized that we have evidence that every big galaxy develops one of these big black holes. This energy of the formation of the black hole must be released during the growth of the black hole early in the history of the galaxy. And people have tried to figure out how that would all fit together with the formation of stars and galaxies. This is it's about a minute and a half from an effort, major collaboration based at MIT called Illustrious. And what it's going to do is it's going to illustrate how galaxies might have developed starting about 2 billion years after the Big Bang. This is mostly dark matter here. This is not yet the stars that are formed. As gas falls into these regions, which are going to become galaxies, and as it does so, these black holes form and grow. So I'll set this into motion and hope that it doesn't stall. The rotation here annoys me, but it's meant to, it's just the camera that's moving around to give the impression of 3 dimensions and to show that we're looking at a 3-dimensional thing. And what you see here is fireworks starting as these galaxies form. So it's not really a matter of stars forming and that's it. But what's happening is that as the gas collects in these galaxies, some of it's forming a black hole, and as the black hole forms, it's releasing these huge eruptions. And what these eruptions are doing is it's actually blasting most of the gas out of the galaxy before it has a chance to form stars. The color coding here is, I don't remember exactly which color is which, but it's a combination of temperature and composition. So it's a little bit complicated, but the main thing is to get an idea of the dynamics that's going on here. So 8 or 9 billion years after the Big Bang, we have lots of fireworks as these galaxies form. This was presumably the era when we think most of these black holes formed. After that, and getting into the modern age of the universe, which is now about 14 billion years after the Big Bang, everything's much quieter. We have all these black holes because you can't get rid of them once you form them, but for the most part, they're sitting there and not doing very much. And it's going to sort of stop there. So that's about 11 billion years after the Big Bang. Okay, so you might think, bad, you're destroying these galaxies. They're not going to be anything like what we observe. But actually, what the evidence is that we actually need this feedback. Because people have also run these models without the feedback. And what they find is if you compare the sizes and numbers of galaxies when you don't have these black holes shooting off with what happens when you do have these black holes, without the feedback, it doesn't fit. So on the left, without feedback, the blue is the actual numbers of galaxies of different sizes. So big galaxies on the right, small galaxies on the left. You see that there's a pretty sharp cutoff where you don't have a lot of galaxies bigger than about the size of the Milky Way. If you don't have this feedback, you would predict a huge number of galaxies much bigger than the Milky Way, which would have all formed stars very early in their history. And then they would have used up all of the available raw materials for forming stars, which is gas, and they would have just turned off. We say that such galaxies would be red and dead, and your average galaxy is actually not. So with feedback, you prevent that from happening, and it actually fits pretty well. And there's also this excess of galaxies on small size. Getting rid of those is a somewhat different story. It has to do with stellar explosions like supernovae. So that is probably not related to black holes. So actually, black hole feedback, as seen in that animation I just showed, is actually a good thing if you want to understand how galaxies formed without becoming too large and forming too many stars. Now, there's another clue that this feedback thing, there might be something to it, and that is that there's a pretty tight correlation with the mass that's found in any given galaxy and how strong the gravitational field of that galaxy is. The strength of the gravitational field is measured by this parameter sigma, which has to do with how fast the stars are moving around inside the galaxy, because that's affected mainly by the gravity of the galaxy. So we call this the M sigma relation. You sort of see that galaxies with stars moving around faster have larger mass black holes. And it's a very steep effect. It goes like the 5th power of the speed of the stars in their motions. You may ask, why is that relevant to feedback? Well, it suggests that the stronger the gravitational field, the more energy you need to regulate the star formation. Because, I mean, the gravitational field is what's trying to pull the galaxy together. And if you think that that galaxy is going to form too many stars unless you have this feedback, you need more energy to prevent that from happening. and thus a bigger black hole. So that's one way of trying to explain that. But in fact, it's really up in the air. We think that there is a symbiotic relationship between the black hole in the middle of the galaxy and the galaxy itself, but we don't know if the black hole is the chicken or the egg. And I don't know if this is really a good analogy, but what I mean is we don't know if the feedback from the black hole limits how many stars actually form in that galaxy, or whether the black hole limits its own growth by turning off the mass supply, and that limitation depends on how big the galaxy is to begin with. So it's a little bit complicated, and this is actually a very active area for research. Now, what about the current state of activity at the center of the Milky Way? Well, it's, as I've said, it's pretty meek. This is a time-lapse image of the center of the Milky Way. This location of the center of the Milky Way is usually called Sagittarius A star. It's in the center of the Milky Way. It's in the constellation Sagittarius on the sky. Right now, the Milky Way's black hole is very quiet. It just does these little blips in infrared, seen here, and also occasionally in X-rays. But it's very quiet because right now it's not swallowing very much. And even though there's a fair amount of gas around, the gas is, swirling around pretty fast. There's a lot of stars exploding near the Milky Way. The gas is stirred up. It has trouble getting into the central black hole. But there's every reason to believe that the Milky Way could flare up someday. We saw some evidence that it probably flared up in the fairly recent past, and a few million years ago is very recent by galaxy standards. In fact, we're sure it will, because there are stars flying around everywhere in the center of the Milky Way, including very close to the black hole, as you saw in the first time lapse I showed, which won the Nobel Prize last year. And we know how many stars there are there, so we can work out statistically that every 10,000 to 100,000 years, one of them is going to get close enough to the black hole that it will get torn apart. And in fact, these tidal disruptions of stars by black holes have a very well-defined signature. You can sort of predict how they should rise and fall in brightness as matter is first supplied in the region around the black hole and eventually drains into the black hole, with maybe a jet being produced at the same time. And this characteristic signature has been seen at least 60 times in other galaxies. You can simulate what it would look like. This was done by Eric Coughlin, a graduate student of mine who graduated about 5 years ago. He's now an assistant professor at Syracuse University. And here's one of his thesis simulations. Black hole is the blue dot here, and the orange is the debris from a star that got too close. And so you can sort of see the reason it continues to come in is because some of the gas released by the disruption of the star initially got out to very large distances and got stretched out by the black hole's gravity as it fell back in. But you end up with a big mess, which lasts for about two to 3 years. And during that 2 to 3 years, the Milky Way's central black hole could become quite bright. But the whole process is only one star's worth of debris, so it's actually not going to do all that much damage to a galaxy as a whole. So we can speculate a bit about what would have happened if we didn't have the feedback in the center of the Milky Way or any other galaxy, but we know we're here. So what would have happened if there hadn't been a giant black hole forming as the Milky Way formed? Well, as we saw before, if you don't have that feedback, we probably would have been in a much bigger galaxy. Star formation would not have been parsed out as it was. Okay, it would have, the gas forming the Milky Way would have come in, formed stars very early. That would have been it. That might have been great. We could have formed the solar system early, and maybe our civilization would be doing something else right now if we survived, or maybe we would have been done billions of years ago. So Milky Way might have been a much larger galaxy, but maybe the conditions for the development of the solar system and a planet with life would not have been so great. The early solar system would have been surrounded by many more stars and probably many more massive stars, because part of the star formation over time allows a lot of chemical elements to build up, and like carbon and oxygen and things like that. And we know we need those for life, so you need those on a good planet. On the other hand, when you have a star that has not had a chance to form all those chemical elements, it tends to be a more massive star, and more massive stars are more explosive. So the early solar system would have been bathed in debris and radiation from a lot more exploding stars. So maybe that would have been a bad thing for life on the early Earth. Might have sterilized the Earth, might have vaporized the oceans. There would have been more stars flying past the solar system. My colleague in APS, Angela Anne-Marie Madigan, studies what happens when you have gravitating bodies interacting with each other, even at a fairly large distance. Gravity is a long-range force, so our solar system would have been disturbed a lot more by passing stars. That might have destabilized the solar system. And one thing it might have done would have been to send more comets and asteroids into the center of the solar system and into the Earth. So we might have had many more violent extinction episodes. Maybe that would have been good, but that certainly would have been different. And furthermore, the Milky Way would have eventually become red and dead, meaning that if you had any of these disturbing effects in the first three bullets here, there would have been less remaining gas to repair the damage later on when things quieted down by maybe creating a new solar system. And our solar system is only about 4 or 5 billion years old, I think. So things might have been a lot different if there hadn't been a black hole. So you can speculate on the consequences of black holes, even for our existence and for astrobiology in general. So that's pretty much what I wanted to say, just to give you a takeaway. I hope I've given you the idea that the interactions of black holes with their environments are pretty complex, but pretty intriguing, and that these things that most people think are cosmic vacuum cleaners are actually pretty fussy eaters, even if you place a meal right in front of them. And when they do eat, which does happen, they make a huge mess. And that this mess involves an enormous amount of energy, so much so that even this little black hole that's a tenth the size of the Earth's orbit at the center of the Milky Way, 25,000 light years from us, would have had a fundamental effect on our current cosmic environment. So thanks. I'm happy to take questions. And thanks for the invitation.
Thanks. Maybe I can encourage. Can you hear me, Mitch? This is Andrew.
Yes.
Andrew Hamilton, Mitch's colleague, speaking. Mitch asked me to have a look at watch the chat, and I can see that there's a whole number of questions already on the chat. If you would like to unmute yourself and ask your question directly, please feel free to do so. But in the meantime, let me start off with some of the questions that are already in the chat. The first one was, you earlier mentioned that most of the merging objects that have been seen in gravitational waves so far are black holes and black holes. And then there's a couple of neutron stars and neutron stars with black holes. How can you tell the difference between the merger of black holes and neutron stars?
I believe that at this point it's entirely determined by the masses of the objects that are merging. So we know that no neutron star can be more massive than about 3 solar masses, whereas we think that no stellar mass black holes are less massive than about 6 or so solar masses, and most are much more massive than that. And so I think we don't have any discriminant that's better than that. I mean, you would think that since a black hole is pure curved space-time and a neutron star is a physical object, there would be tidal forces, and you could tell, the neutron star would get distorted in a different way than a black hole just before the merger took place. But I believe they do not have enough discrimination to detect that yet. I could be wrong. I'm sure they're trying to do it, but I think it's entirely based on the masses. And even when you try to get the masses of the two objects, there are these signals from these merging objects are sufficiently detailed that you have a lot of ways to figure out the properties of the system before the merger occurred. There is still some uncertainty about the masses. So it took quite a while, for example, before they decided that the 3 black hole neutron star merger events that have been seen were actually black hole neutron star events and not black hole mergers.
There's another question in the chat from Bob Grossman, who asks, how does this knowledge affect your approach to everyday life?
I have I have a deep sense of the universe being very big, and I don't think that there's any fundamental significance to the Earth as far as the universe is concerned. We sort of operate in our own local system, and that's important to us, and then of course it's important to me as well. But I certainly do not have any spiritual or religious sense about our place in the universe. But I'm amazed, and I believe that what we've figured out about how this works is very beautiful and really amazing. And I know that there's a lot of it we don't understand yet. Maybe
I can ask a question of you myself.
Actually, I'd like to ask the same question of you, Andrew. Since you look at a different set of questions about black holes that are perhaps even more exotic. Well, they are more exotic.
Well, Mitch, if you want to push me into a black hole, that would be one way to do this. But I would like to refocus the light upon you on this particular occasion. You mentioned earlier that our Milky Way contains perhaps 100 million stellar mass size black holes, but only one giant black holes. Mm-hmm. And it makes you ask the question, what's so special about this giant black hole? Why should there be only one of them? And why should it be at the center of the galaxy?
Yeah, actually, that's a very controversial and active research topic. We do not have a theory for how these giant black holes formed that everybody agrees on. There are two main schools of thought. One of them is that you start out with very active formation of rather big stars early in the history of the galaxy, and they're big stars because you don't have a lot of carbon and oxygen, and the less of those elements you have, the bigger stars you tend to form. And then these stars formed in a sufficiently tight cluster that many of them merged, and at the same time pulling in a lot of gas, and so you build up these black holes from the collapsed remnants of stars. On the other hand, there's a problem with that theory, and that is that we know that there are some huge black holes that formed so early in the history of the universe that there is not enough time to build up those sorts of masses from merging stellar mass size objects. And so people think that merger theory is not necessarily, it's not supported by the evidence. So the alternate theory is that you form this in the center of a galaxy because the center of a galaxy is like the center of mass of a huge amount of converging material. I mean, a galaxy does not form through lots of different centers. Well, it does form through mergers of subunits, but there are definite centers of mass where a lot of matter accumulates. And if you can get that matter to come together and form a really big object, like people call it a supermassive star, a star that's 1 million times the mass of the sun, that can collapse to a black hole, which is 1 million times the mass of the sun. So the other school, that's the second school of thought, which I belong to, and one of the things my colleagues and I have worked on quite a bit is how this process might work. But the idea is that there is a natural congregation point for a lot more gas at the center of mass of the galaxy than there is further out, say in the equivalent region to where the sun, the solar system is now. So it's just an effect of how gravity tends to work. It tends to pull things together.
Thank you, Mitch. I should mention that there's a whole bunch of comments thanking you for your presentation in the chat. So that's by far the most number. I have another question from Brianna Unzis, asking, saying thank you. Do the same dynamics, falling towards the black hole, heating up, potentially radiating or getting pushed out, does it hold if a solid body gets close to a black hole, for example, a planet with little or no atmosphere? What happens then?
Well, that question, you can think about that tidal disruption of a star. That's kind of a similar thing. If you have a black hole with an intense enough gravitational pull to pull apart an entire planet, yes, that's more or less what would happen. The problem is that you need a very, very large, very intense, we call it a tidal force, a gravitational field that's changing very sharply over a small distance. It turns out that in order to pull apart a planet, you actually need you have to get close to a fairly small black hole. So a black hole of 1 billion times the mass of the sun won't even pull apart a star. A black hole like the one in the center of the Milky Way will pull apart a star like the sun, but probably would not pull apart a planet. Actually, it would just about pull apart a planet. I take that back. Anything with the density of, say, rock would be pulled apart if it got close to, but not inside, the black hole at the center of the Milky Way. So the answer is yes. You could get a planet being disrupted if it got, say, 10 times outside the event horizon of the black hole at the center of the Milky Way.
There's another question here from Maggie Jolmer, who asks, do we know why Sagittarius A star flickers? Is it an asymmetrical accretion disk?
That's a great question. And actually, my colleagues and I and Jilla just had a paper accepted trying to explain this, or maybe it's not quite accepted yet, but we're revising a paper on exactly this topic. We think that there is something asymmetric going on. And as I showed, there are data from this this telescope array in Chile, which gives us an indication that some spot of material is orbiting close to Sagittarius A star. What I didn't say is that when that was detected, the Sagittarius A star was seen to flicker in a particular way. And we think that what is going on is that there are regions of very strong magnetic fields that spontaneously form in some of these disks under certain conditions. And what we're seeing is a bundle of very strong magnetic field orbiting around and basically heating up the gas in a very localized fashion. And it's sort of gyrating around and flickering because it's under the influence of the black hole's gravity. So we think that there is a mechanism that explains the flickering. One of the objectives of our paper was to explain the relationship between the infrared flickering and the X-ray flickering, which is something that many people have been trying to explain without too much success. So we think maybe we've made a little bit of progress in understanding the physical mechanism. But right now it's a theory, and we make some predictions about what future observations should tell us. So maybe we're right, maybe we're not.
I noticed the chat is getting longer than we are able to shorten it. One of the questions that came up is, will my son be able to watch this presentation? He would love to watch it. And I believe it is being recorded. I'm not sure where you will be able to find this out, but somebody will be able to tell you where it's being recorded. Mitch, do you know the answer to that?
I watched some of the previous presentations on linked to the Retired Professor Association website. So I assume this one will be in the same place. Is that anyone who is actually setting this up know? Yeah, I mean, I was able to find these previous presentations online without any problem.
Okay, I'm going to keep going asking you questions until I'm told to stop or until we get exhausted. So the next question is, do stars form in the jets?
Probably not in the jets. These jets are very fast. These jets carry a small fraction of the matter that's trying to get into the black hole. And so they're just not dense enough to form stars. Stars are condensations that are created by gravity locally. And so you actually need fairly dense gas to get a star to form. Interesting thing though is that when a black hole tidally disrupts a star, you get a streamer of gas, which I think was in that animation that I showed, very narrow streamer of gas. And one of the things that Eric Coughlin, my former graduate student, worked out was that those streamers of gas can get dense enough to form condensations, not necessarily star-sized condensations, but his suggestion was that you could actually form free-floating planets in such a stream. So maybe that could work. But that's not quite a jet. That's just the debris from a star that's being torn apart.
Natasha Kellett asks, for a supermassive black hole, would it be possible to pass the event horizon without even knowing it? I'm thinking the tidal forces would be small if the event horizon were huge.
Yes, no, definitely. For example, the black hole in the center of M87 is 6.5 billion solar masses. So it's, as I said, it's 1,500 times as big as the one in the Milky Way. And if you were to fall into that black hole, you wouldn't notice the event horizon. The tidal forces would not be significant. However, once you do that, you are doomed to keep going towards the center, and eventually you would be subject to, you wouldn't make it. I mean, you would be subject to some destructive forces. I hesitate to say you would fall straight into a singularity because Andrew would tell me that that's rubbish. But something bad would happen to you eventually. But you'd have a few hours before that happened inside the black hole.
Dave Nesbitt asks, early on you showed a nice picture of a black hole with observable radiation emitted from the surface. He asks, is this in any way related to Hawking radiation?
No. No. If you mean, I'm not, well, I mean, I showed a few images. There was one that was a visualization by Andrew Hamilton of light being bent around a black hole by the curvature. This is an effect called gravitational lensing. That actually has nothing to do with anything coming out of the black hole. That's all radiation of material, radiation that's passing by the black hole that's being focused into our line of sight to make this pattern. The ring of light that is the image of the M87 black hole is actually not an image of the event horizon. What it is there is a region outside the event horizon where light rays passing by tend to get trapped and basically can go into orbit around the black hole, or at least they can circulate for a long way around the black hole before they go off and then reach us. And so what you're really seeing is this circle of light, and the size of the circle of light is in a non-rotating black hole is about 1.5 times the size of the black hole. The size of the ring of light that we see is about 5 times the size of the event horizon. And the reason it's larger than the actual size of the ring of light is because the black hole acts like a giant lens and magnifies this ring. So you're seeing not the horizon of the black hole, but you're seeing light getting close enough to the black hole to essentially go into circulation around it. And then you're seeing a magnified image of that. So it's a little bit more complicated than saying it's a photo of a black hole, but I didn't think I had time to try to explain that. You're muted, Andrew.
I'm going to have two more questions, and then anyone who wants to stay behind and ask Mitch personally is welcome to do so. The next question is from Nick Conant, who asks, does the ejected mass from a supermassive black hole's activity fall back into the galaxy itself, or does it get lost in intergalactic space?
We think that actually is a pretty complicated question that depends more on the nature of the structure of the galaxy and its surroundings than it does on the structure of the jet. We see evidence for both happening. So I showed you a picture of an entire cluster of galaxies where everything in the cluster between the galaxies is getting stirred up by the activity of the black hole. So there, the energy is really escaping the galaxy, and it's spreading out over 1 million light years, and it's probably escaping the cluster of galaxies. So that's a case where it has a clean shot out. And probably one of the reasons for that is that the galaxy where these jets are being produced is a galaxy which actually does not have a lot of dense clouds of gas in it. So that's a galaxy that, somehow managed to form a pretty clean ball of stars without having a lot of gas left over. Whereas in the Milky Way, it's likely that the jet is going to run into so much material that it's going to get slowed down before it gets out of the galaxy. So it's not that likely that you get most of the energy from the Milky Way's black hole going into intergalactic space.
Last question. This is from Brian Cashian. One theory of dark matter is it's due to primordial black holes. What do you think about that?
It can't be ruled out. There are observational constraints. There are things you can say about what the masses of these black holes could or couldn't be. There are issues about how they might have formed. One thing we can say is that they are not black holes they couldn't be black holes that are less massive than about the mass of about the mass of Long's Peak, which is, I forgot what that is, but you can imagine a cube of dirt of a kilometer on a side. Okay, so any black hole of that mass, which would be the size of a subatomic particle, that mass or less would have evaporated by Hawking radiation already. And if there was a significant population of those black holes currently in the universe, they would be evaporating as we speak, and you'd see the gamma ray flashes from those. So we know that, according to everything we understand about Hawking radiation, we know that the dark matter is not those black holes. On the other hand, they can't be more massive than, say, a few 100,000 times the mass of the sun, because those actually would make too much disturbances to the orbits of stars and galaxies, and would just make galaxies look different than they do. But in between those two limits, it's actually difficult to say. The main issue is that nobody has a good way of having formed those a population of black holes like that would be abundant enough to explain the amount of dark matter that's in the universe, which is a lot larger. So, for example, these black holes could not have been formed from ordinary, what we say is baryonic matter, atomic nuclei. They couldn't have been formed by the collapse of those sorts of objects, because in the early universe, we know the maximum amount of baryonic matter that could have formed.
Okay, I think that's an excellent point on which to conclude this. And let's thank Mitch once again for an inspiring and imaginative colloquium. Thank you very much, everybody.
Thanks.
Let's see, this is Dave Cassoy again. I'd just like to remind everybody that this is one in a series of talks, and they will continue in the next months. So be on the lookout for messages from the University of Colorado Retired Faculty Association Boulder campus for scheduling. They'll usually be on Wednesdays at 7 p.m. And we're hoping to sort of establish that as a normal hour so that people can be recognized when things are coming their way. Thank you very much for participating and listening. We hope you enjoyed it. I certainly have enjoyed it. And I hope there'll be more intriguing presentations in the future. Thanks a lot and good night.